So in a previous video, we introduced this concept of electron configurations, also called spectroscopic notations or SPDF notation. And in that notation, we specifically gave the address for each electron in an atom, dependent upon the orbital that it was residing in, either a 1s, 2s, 3s, or a 2p, 3p. We used those orbitals in that full electron configuration. So when writing electron configurations for atoms, you could guess, particularly when we got to the iron example, that when you start adding electrons to atoms, that your electron configuration can get pretty lengthy. So that is one reason why chemists like to make use of this noble gas notation. It's sort of a shorthand method for writing electron configurations. If you want to think about an electron configuration as synonymous to an address for a particular electron, where you actually write out the words street and avenue and quartz and place, parts that are part of an address, think about this noble gas notation as like doing abbreviations for those longer words. The way that we do abbreviations for this noble gas notation, our abbreviation comes from representing core electrons. Specifically, we represent core electrons by writing the noble gas that represents those electrons. So for example, if I wanted to write the noble gas notation for oxygen, well, I know the full electron configuration is 1s2, 2s2, 2p4. To write the abbreviated version, I look to see what the closest previous noble gas is for oxygen. And I see that it is helium. So instead of writing 1s2 for my electron configuration, if I'm doing the noble gas notation, instead of writing 1s2, I just put the symbol for that noble gas, specifically helium, in brackets. And then the rest of the electron configuration is as what you would do for a normal configuration, 2s2, 2p4. But for potassium, the full electron configuration is written down here. If I was to write the noble gas, sometimes also called the abbreviated electron configuration, I look to see what the closest previous noble gas is for potassium. Oh, that closest previous noble gas for potassium is argon. So I put argon in brackets. That takes care of all of these electrons that are in blue for the longer electron configuration. And what I write is just what's left, 4s1. So noble gas configurations let us easily determine the numbers of core electrons for an element. These are electrons that do not participate in bonding. In subsequent videos, we're going to talk about valence electrons a lot more, because valence electrons, those are the ones that are obviously not core electrons, but valence electrons are the ones that do participate in bonding. So noble gas notation, you put closest previous noble gas in brackets. That represents the core electrons for that element. And then you write the rest of the electron configuration as you would normally. So let's go ahead and let's do some examples on the next slide. Let's go ahead and do phosphorus. Phosphorus, I look at my periodic table, which I hope you have in front of you. Phosphorus, it has atomic number 15. So I need to account for 15 electrons. I'm doing the noble gas notation, so that means I need to first put in brackets the closest previous noble gas to phosphorus. That closest previous noble gas is neon, so I put neon in brackets. And then I do the rest of the configuration as I would normally, 3s2, 3p3. For manganese, my 25 electrons, atomic number 25. My closest previous gas is argon. And then I have 4s2, 3d5. So this tells me that in this manganese atom, I have a total of 18 core electrons. Promethium all the way to 61. Oh, so we're down by where the f orbitals are. Looking at that, I see that my closest previous noble gas is xenon. And what I'm left with after xenon, which takes care of electrons 1 through 54, what's left after that is 6s2, then 4f5. So you should feel comfortable being able to do the noble gas notation for a particular element, as well as its full spectroscopic notation or electron configuration.